Okay, so welcome back to part 2 of section 3.2. We're still working on solving linear programming problems. We're graphing feasible regions, and we're finding the value of an objective function at the corners. All right, so here I have another example where they've done the graph for us. They found all our corners, and our job is to, I'm going to do this one this time, find the maximums and or the minimums values for those objective functions for that feasible region. Right. So I've got my corners. I'm going to label my corners A, B, C, D, and E. Don't forget about 0, 0. That is a corner. And I'm going to go ahead and evaluate this objective function and all of those. All right. So at corner A, what's the value of Z? Well, it's going to be 1.5 times X, which is 0. Plus 0.25 times y, which is 12. 12 quarters is $3, so 3. And then I'll find the value of the objective function at b. So z is equal to 1.5 times 4 plus 0.25 times 8. 1.5 times 4 is 6. 0.25 times 8 is 2. 6 plus 2 is 8. Now I'll find the value of the objective function at corner C. Z is equal to 1.5 times 7 plus 0.25 times 3. Let's see, I'm going to need a calculator for that. So where's my calculator? There it is. 1.5 times 7 plus 0.25 times 3, and I get 11.25. And now I'll find corner D. The value of z there is going to be 1.5 times 8 plus 0.25 times 0. 1.5 times 8 is 3 times 4, that's 12. And then the last one I have to do is I have to do corner E. So E is going to be, z is going to be 1.5 times 0 plus 0.25 times 0, which is 0. And now my job is to find the biggest and also the smallest this time. So it looks like 12 is the biggest. So there's my max, and 0 is the smallest, so there's my min. So we would say that the objective function is maximized at, and where is it maximized at? Point D, okay, 8, 0. With z equal to 12 and minimized at 0, 0 with z equal to 0. Okay, not too bad. All right, let's take a look at the next one. All right, and this is our last one for this section before 3.3, but we have to do everything. So let's take a look at what's been given here, and let's give it the language of linear programming. I am given an objective function that I am going to optimize by maximizing, subject to my constraints for my system. Okay, so I'm going to go ahead and graph this feasible region. Okay. Again, I'm going to call them 1 and 2 and 3 and 4. Okay. The boundary line for 1 is going to be 2x plus 3y equals 100, which means it's going to cross the x-axis at 50 and the y-axis at 33 1/3. Right? The boundary line for equation 2, or for inequality 2, sorry, constraint 2, 5x plus 4y equals 200. It has an x-intercept of 200 divided by 5, which is 40, and it has a y-intercept of 50. Now, these are kind of like the non-negative conditions, so I'm not going to worry about boundary lines for those. I'm just going to worry about the other boundary lines. So it looks like my x-axis needs to go out to 50. And let's say about 10 there, 20, 30, 40. My y-axis needs to go up to 50 also, so we'll put 50 up there. And then we've got 10, 20, 30, 40. So 10, 30, 50. So then my boundary line for my first one goes from 50 on the x to 33 1/3 on the y. And I want less than that, so I want the smaller side. So I'm going to shade this side over here. And I'm going to use a simplification to my shading process so that I don't have a whole bunch of colors kind of overlapping and making it ugly. My boundary line for my second inequality goes from 40 on the x-axis to 50 on the y-axis. And so they're going to intersect there. And I want less than, so I want this side. So I'm already limited down to this trapezoidal piece. Okay, then how do I deal with these last two? Well, this one says that I need x's that are bigger than 10, so that's going to be a vertical line at 10, and I want to the right of that. So now it looks like I'm just in this piece right here. Okay, and then that last one says that the y's need to be between 0 and 20. Uh-oh. See, here's the problem with trying to draw this by hand. Where does that intersect? Does it intersect above it? Does it intersect below it? Does it go right through it? I can't really do this one well enough by hand, accurate enough by hand to make this useful. Okay? The intersection point there is just too close for me to feel comfortable, because if I put it below and it's supposed to be above, or if I put it above and it's supposed to be below, I'm going to have corners that don't exist, or I'm going to miss corners that should exist. So realistically, I need to take this thing over and throw it into Desmos. Okay. So I'm going to grab this, but I'm going to go to Desmos. I'm going to see what I can do about trying to make this work nice. So maybe if I put it half and half, would that work? Okay. All right, so my first inequality is 2x plus 3y. It should be less than or equal to 100, but I'm going to shade the opposite side again to make it easier to see. My second inequality, my second constraint, if I want to get fancy about it, plus 4y is greater than or equal to 200. My third inequality is x is less than or equal to 10. Remember, I'm shading the opposite side. Now my fourth inequality, that's a tricky one because I can't just change the direction of those two. I have to see this as two inequalities. One inequality is this, or probably easier to read, y is greater than or equal to 0, which I'll graph over here as y is less than or equal to 0. The other inequality that's hiding in there is the other half, where it says that y is less than or equal to 20, which I'll graph down here as y is greater than or equal to 20. And now I'm going to come over here. I'm going to hide that because I don't need that anymore. I'm going to make this as small as possible, and I'm going to say that the unshaded piece is my feasible region. So let's make it fit as big as I can in here. And then let's use Desmos to find us all those corners. There's a corner there, corner there, corner there, corner there, corner there. Right? So I've got corners of, and if I just label them starting in the upper left as A, B, C, D, I'm just going to go ahead and copy them down over here on my picture. Let's see. This was 10, 0. Then we had one up here that was 10, 20. And then I have, my graph is so bad that I don't even want to use it. I'm just going to label them down here, A. So starting in that upper left-hand corner, 10, 20, B, 20, 20, C, 28.571, comma 14.286, D, I like that one better, 40, 0, and E, 10, 0. All right. So now that I've got my corners, I'll make this big again, and I'll come back over here and I'll find the value of my objective function at each of those corners. So at this corner right here, what's Z worth? Well, remember, Z is up here. It's 10 times X plus 8 times Y. So that's 10 times 10 plus 8 times 20. Okay. 10 times 10 is 100. 8 times 20 is 160. So I get 260. We good to there? Second corner. 10 times 20 plus 8 times 20. 200 plus 160. 360. Fourth corner, I'm going to skip the third corner and come back to it. Z is equal to 10 times 40 plus 0, 8 times 0, or 400. Down here, I've got Z is equal to 10 times 10 plus 8 times 0, 100. So right now looking like D's the winner, but I got to figure out C. Okay. C is going to be Z equals, and that's a calculator problem if I ever saw one. I got to do 10 times 28.571 plus 8 times 14.286, and I get 399.998. Now, here's where I got to be smarter than the system. I rounded these, didn't I? Okay. In fact, I'm going to go back to Desmos and I'm going to look at that again. This point right here, that's the intersection of the blue and the green. It's the intersection of these two first equations, the boundary lines for those first inequalities, right? And so what I need to do is I need to find out what the coordinates of that point really are, okay? Because here's what I'm betting. My bet is that this corner down here and that corner up there on that green edge right there, my bet is they have the exact same Z value, and we're going to have to parameterize this solution. All right, so I've got to find out the actual intersection of 2x plus 3y equals 100 and 5x plus 4y equals 200. So I need to solve this system any way I can. Now we just got done doing a whole bunch of these using the calculator back in chapter 2, so I'm going to do that again. So here's my calculator. I'm going to go to my matrix. I'm going to edit that matrix. That's a 2 by 3 matrix. The entries of the first row are 2, 3, 100. Second row is 5, 4, 200. I quit out of there, go back to matrix, over to math, RREF, because I'm going to Gauss-Jordan this thing. There's those horrible decimals, but if I turn them into fractions, I find that x is equal to, what did it say again? 200/7 and 100/7? Okay. Where are we at? Oh yeah, I found out by looking at the graph that every point on this entire edge between those points is going to be a maximization of my system. So now I need to parameterize my system. Okay? That green edge is the boundary line, 5x plus 4y equals 200. So if I come back over here, I'm going to say that my final solution is that we are maximized at z equals 400 anywhere on that boundary line. So on 5x plus 4y is equal to 200, but only for x's between those values. And where did I get those from? Those are the x values of the 2 points. So anywhere on that line, as long as x is between those numbers. And if you knew the value for x, you could put it into the equation there. So if you pick a number between 207th, which is 28 and change, so let's say you picked 30, you could plug it into this equation, you could find y, and then you could say, okay, then if x is 30, so that means you got 5 times 30 plus 4y equals 200. That's 150, so 4y is equal to 50. Y is equal to 12.5. The point 30, 12.5, if you put it into z, you would get 400 as well. Okay. Now this thing that we just did right here, that's rare. It probably won't happen in your homework. It probably won't happen in your exams. When you run across the problem in the homework that you think you have to find a parameterization of an edge, think twice about it, because you might not be. All right, I'm going to stop this video here. We'll come back, and the next video is going to be the next section, section 3.3, where we're going to solve that cake cone and sugar cone problem. All right, I'll see you back here for section 3.3.